Hi everyone. My name is Lakshmi Thapa. I'm the president of ISPRS Student Consortium, and we are here for the first webinar series of the first ISPRS webinar series for the year 2023. And our topic for today's webinar is the Alaska Satellite Facility radar-based Earth observation from the center of Alaska. And before moving to the core webinar presentation, I'd like to give a brief background about ISPRS and its activities, and just a brief guideline about the webinar. Please introduce yourself, as I have already mentioned before, and we have a Q&A session that you might see just next to your chat box. Please feel free to post your questions there and try to make it to the point and as minimal as you can. And also, if we have enough time, you can raise your hand and ask it on your own too. And we'll try to send one evaluation form once the webinar ends so that we can get feedback from you all for the improvement. And talking about ISPRS Student Consortium, well, it's the official representations of the youth to ISPRS that aims to link students, young researchers, professionals worldwide who are interested in photogrammetry, remote sensing, and spatial information science. And it also aims to promote scientific and professional development at the same time while advocating imaging and geospatial science for the informed, scientifically valid, and technologically sound observations of Earth conditions. And it also aims to help in effective decision making. Talking about current board of directors, you can see myself as the president, and also Sunny has joined us. You can see he's our newsletter editor-in-chief, and Yogender is our website administrator. At the same time, we have Nicholas, Miguel, and Tsukuma joining in different positions, and we all are from different parts of the world. Talking about our activities, we are publishing newsletter. So far, we are publishing 4 issues in each volume in each year, and the recent issue that we published is application of close-range remote sensing for forestry. And our upcoming issue is about application of geospatial technologies in social media data analysis. So if any of you are working in this topic or in this domain and would like to submit your article, please feel free to send it. It's free and you don't have to follow a core journal-based guidelines. We publish it on an article basis, so it can be a Word document containing a page of your research summary. And then talking about other activities, we have been organizing summary schools, and this is like one of the core activities that we have been doing. And every year we try to sponsor 3 of the summary schools from our side, while at the same time we partner with different organizations to organize more summary schools every year. And these are some of the screenshots of past summary school we organize. And there are a few more summer school coming this year from our side. We're still in discussion with few of the organizations. The one that has been fixed is about optical instrument, that is like summer school about optical instrument handling, that is going to happen in Italy soon. We'll post about that event in our chat box very soon. And talking about other activities, in the past, we have been organizing ISPRS Student Consortium virtual rooms, and also ISPRS Student Consortium webinar series on which you are joining us at the moment. So the main objective of this webinar series is to diversify the means of information and knowledge dissemination within ISPRS Student Consortium, and also to act as a way of connecting ISPRS Student Consortium members with the wider ISPRS community of scientists and professionals, and at the same time to maximize the available expertise within the community by enhancing the learning experience. By enhancing the learning experience of the members of its community. And then talking about our past ISPRS Webinar Series and other events that we have been organizing. We are putting all of our recordings on our YouTube channel. You can search our YouTube channel in the name ISPRS SC, and you can see all the videos there. And our YouTube channel is getting popular too, so you can see a number of views for the webinar we have organized in the past, and we'll upload this recording too on our YouTube. Talking about other activities, we have organized GeoMixture by partnering with different organizations like Ladies of Landsat, Sister of SARS, ISPRS, GRASS, and other related organizations to connect people from different parts of the world with each other during the time of pandemic. At the same time, one initiative that ISPRS Student Consortium organized was Leadership and Service Mentorship Program, and some of the current board of directors are the product of that service Leadership and Service Mentorship Program. And if you want to be in communication with us, and if you want to see the activities that we are organizing, you can follow us on our different social media channel. We are active on Facebook, YouTube, Twitter, and we also have Instagram page on our name. I forgot to put it here, but we'll post it on our chat box later on. We have our one official website, which is updated regularly, and you can see our activities there too. And just a notice that we are still in search of volunteers. So if you would like to participate or if you would like to join our team, we are still looking for a design volunteer and proofreading volunteer. Feel free to email us if you have experience in it, and if you want to see how international organizations, professional organizations like ours work. Now we'd like to move towards webinar, and as I mentioned earlier, our topic is more about SAR technology, and I think we have speaker with ourselves, so I'll not go through the abstract as he's going to present it more. And just to mention you about our speaker, we have Dr. Franz Meyer with us, and we're really honored to have him with us, even despite his busy schedule and from being in different time zone too. So thank you so much for joining us. And I think your name is enough in the field of SAR, and I don't need to explain more about your experiences. And I'd like to hand over the screen to you now. Yeah, over to you, Dr. Meyer.
Sounds good. Can you all see and hear me?
Yes, we can see you and hear you.
Can you hear me also?
Yes.
Okay, excellent. Let me share my screen. Give me a sec while I pull this up. Let's see. Do you see full screen?
Yes.
Okay, let me.
Yes, perfect.
Participant list in the chats. Okay. Well, welcome to all of you for this short presentation of mine about the Alaska Satellite Facility. So my name is Franz Meyer. I'm here in Fairbanks, Alaska, just close to Blinds, but Alaska is right behind me. I'll talk a little bit about early on about who I am, and then talk about where ASF is and why we are in the place where we are, and then talk about two types of activities that ASF is doing. One more is activities that relate to services to the community. I'll emphasize the work we do to make SAR data sets easier to access and easier to work with. And then in the second part of it, I'm going to talk a little bit about some of the research we do, our own research with SAR data sets, mostly in the field of hazards and geophysical analysis. So let me kick this off. Just starting out with a few words about myself. Let's see if my computer is catching up with me. Okay. Let me turn on my laser pointer. Okay. So I grew up in Germany. I got a degree in engineering. So I'm working now in a geophysics department, but I'm really just a pretend geophysicist. In my heart, I'm an engineer. I got a master's and a PhD from a university in Munich. Then I worked a few years at the German Aerospace Center in the TerraSAR-X team, where we were developing the processing algorithms that are behind TerraSAR these days. Some of you may have used TerraSAR data in the past. And then in 2007, moved over to Alaska, where I have two roles. One part of my life is as a professor at the university, where I do a lot of education and training and my own SAR-based research. And then my other part of my appointment is as the chief scientist of the Alaska Satellite Facility. So I'm responsible to communicate with the science community and help direct ASF's work that's related directly to the scientists. So just a little bit, a word on ASF itself, and I want to give you first a sense of space of where we are. So this little fly-through brings you to where ASF is located. We are in the heart, in the center of Alaska, on the campus of the University of Alaska Fairbanks. So we are at very high latitude. We are almost at the polar circle, just a tad south of the polar circle, and fairly far in the west when it comes to time zones. Alaska, just a few words about it. Alaska is a very big state. You cannot be from Alaska and have a presentation where you don't point out how enormously large Alaska is, especially. So it's very big. It's about three times the size of France, about 5 times the size of Germany. But at the same time, it's a very empty state. So for some of you that you may not know this, but Alaska, despite its size, has only about 700,000 people. So many of you live in cities that have more people than the entire state of Alaska does. So it's very easy to get away from people when you are in Alaska. Fairbanks itself has a very varied climate, so I encourage you to at some point come up and visit. We have it's one of the cities with the largest variation of temperature throughout the year. So temperatures go from anywhere down to minus 58 degrees Celsius to plus 35 degrees Celsius in a season. Those are the extremes. Mostly will go back and forth between about minus 30 and plus 20 degrees throughout a season. And we have snow cover that usually starts in September and ends in May. So we just last week had what we call Green Up Day, which where the snow goes away and all of the plants are starting to green up. So we're just in the second week where we have leaves on trees, and we are very excited about that. So ASF is in Fairbanks. It is on the campus of UAF. It's in this building over here. So we'll fly real quick to the ASF building. So we are in this brown building and in the building behind it. Should you ever come to UAF campus, you see there's a poorly rendered satellite dish on top of the building. That's one of the ones that ASF is operating. And we have additional downlink and communication dishes here in the woods. Currently, we operate 4 different dishes on behalf of NASA for space communication. So most of you know ASF as a data center. We are a so-called DAC. DAC is an acronym that NASA is using. It stands for Distributed Active Archive Center. NASA has decided that it will house its space-based data sets in various different places that are called DACs. Each of the DAC has a different theme and a different focus. And ASF's is the data center for SAR data. So we are housing and distributing all data sets that either NASA owns itself because they were acquired by NASA-owned satellites, or data sets that NASA has some sort of agreement with. And we'll get to that in a sec. We were founded in 1991. So we've been here now for more than 30 years. And we were originally founded as a downlink station, so to operate these satellite dishes for space communication. We'll get to that in a sec. And so we currently operate 4 actually antennas. We just on-ramped a new antenna that we'll use for the NISA mission. From a data center's perspective, one of the things that makes ASF unique is that we are one of the largest data centers in the world. We currently have about 19 to 20 petabytes of data in our archives. And another thing that makes us unique is that all of our data sets these days are in the in the cloud, specifically the Amazon Web Services cloud. And that gives you high performance access to data sets. It allows you to download data sets very quickly. And it also allows you to actually, instead of downloading data, to work with those data sets directly at the archive and in the cloud and not on your local machine. And I'm going to get to that a little bit too. If you already are using SAR data sets, you may notice you may have worked with us already. We are currently a host of the global Sentinel-1 archive. Sentinel-1 is a C-band radar mission that was launched by the European Space Agency in 2015 and 2016, or 2014 and 2016. And so it's owned by the European Space Agency, but NASA has an agreement. We are a mirror of the archive, and we are currently, I think, maybe the only official archive of Sentinel-1 that has all the data from the very first acquisition to the most current acquisition on live spinning disks. So if you're interested in Sentinel-1 data, you can, of course, either go to our partners at ESA, or you can come to us to access and download those data sets. In a few, actually next year, in January, there's a new mission that's going to be launched. It's a mission that is a collaboration between NASA and the Indian Space Organization, ISRO. We are very excited about this mission. We will be the archive for all of the L-band data sets coming from NISAR, all the level 0 to level 2 data sets from NISAR. And we're working very closely with ISRO on mutual access to S-band and L-band data sets from this satellite. Overall, we have data back to 1978, which was the first spaceborne SAR that was launched, which was CSAT, operated by NASA at the time. So why are we in Alaska? The reason why we are at a high latitude location, or in Alaska specifically, is if you go to high latitude locations, you see an orbiting satellite more often than in lower latitudes. So we can see a specific satellite up to 8 times per day, which allows for very effective space communication to those satellites. And so Fairbanks, where we are located here, was at the time the northernmost location in the United States that provided stable power and stable internet when we were formed. This is actually not true anymore these days, but that's why ASF was founded and built in Fairbanks. So ASF these days does really 3 different things. The main thing, again, that you are familiar with probably is our role as a data center. As the data center, we do 2 things. One of them is our main role really is to take in synthetic aperture radar data sets, archive and sort of curate them and make them accessible to the community. So we have search clients, et cetera, that you can use to discover data sets. Over the last few years, we have branched out to other parts. And the main thing that we do these days as well is we allow you to create certain high-level data sets directly at the archive. As you may or may not, if you have used SAR, you know this, and if you haven't used SAR, you know this probably too. SAR data sets are not always easy to work with. They have very large data volume. They're not geocoded. They need to be calibrated in all of these steps. And they're all computationally very intensive. So we are trying to take all these heavy workloads away from you and let you exercise those directly at the archive. So we have done a lot of work in sort of analysis-ready data products. I'm going to talk about that in a little bit. In addition to the data center role, our second role, as I mentioned earlier, is one as a NASA ground station. We operate for NASA currently 4 satellite dishes. If you are familiar with sort of the wavelengths, those operate at X-band, S-band, and K-band. The newest dishes that we have implemented, they are fully K-band capable, which allows for more data downloads in shorter times. So very high throughput satellite missions, such as the upcoming NISA mission, require K-band download, and we've upgraded some of our antennas to be fully K-band capable. A third thing that ASF does is what we call ASF Enterprise. I'm the director or the lead of ASF Enterprise. ASF Enterprise is a little bit our playground that allows us to develop new ideas, develop new capabilities, and then once we have developed them, to transition them either into the DAC or transition them into the ground station, depending on what capability we develop. So all of our SAR-based research we do through ASF Enterprise. Through ASF Enterprise, we operate an additional ground station. So these are satellite dishes that we own ourselves. And we, through those ASF Enterprise, we can cooperate with organizations that are not NASA. So we've worked with JAXA in the past for data downlinks, and we've worked with many of the commercial data providers and provide downlink capabilities to them. So this is what ASF does. And these days, ASF manages a very rapidly growing archive of free and open, regularly sampled SAR data. And that's a change in the field of SAR that cannot be overstated in its importance. In the past, SAR was always an interesting data set from a scientific perspective, but really to work with SAR in a more application-related perspective, we needed to have sensors that acquired regularly. And so since Sentinel-1, we have now sensors in space that take acquisitions regularly every, say, 6 to 12 days. And we had to make sure that the data sets were of good enough resolution and freely and openly available. And Sentinel-1 has really helped us pave the way toward a complete global archive that's freely accessible for the science and applications communities around the world. And SAR has this fantastic ability that it can see through clouds, it's weather independent, and it can now analyze processes now that these data sets are sampled regularly, better than many other Earth observation disciplines. This example that you see on the right is an area in Peru, in South America, the so-called Madre de Dios area, a rainforest site. Oops, my animation just died. Let me go back and try this one more time. Oops. Do you see the screen flicker? Oh, I'm sorry. PowerPoint just crashed on me, I think. Give me a sec to restart PowerPoint. Oh, sorry about that. I have to stop sharing here real quick and restart PowerPoint. Yeah, we are having technical issues today, so this time it's me. Give me just a second. Can you guys at least still hear me?
Yes, we can hear you.
Okay, give me just a sec. Okay, PowerPoint is back up. Let me share again. Okie doke. We'll get that done, no worries. Okay. Go to the right slide. Okay, I'm getting closer. Okie doke. Okay, so this animation shows you an area in Madre de Dios. As I mentioned earlier, it's a very rapidly expanding deforestation site. This is actually a quite cloudy region in South America, and so the SAR is one of the few instruments that can monitor this kind of deforestation continuously. So it has a much higher relevance these days for many of the applications and hazard applications that you might be interested in. And so this is all due to sensors like Sentinel-1, and the upcoming NISA mission will continue that sort of legacy of free and open data sets. And there are many other missions that are now in the works that will provide similar levels of data access. So we are really excited about this development. Okay. So ASF's mission is then twofold. The first one is to make these unprecedented data volumes that we have available these days accessible to the global research community in ways that are straightforward and as straightforward as possible. And so this is not an easy task, because in a very short time there will be enormous amounts of SAR data sets available. So if you look at sort of our own archive growth, you can see that only like a few years ago, like 7-8 years ago, our archive was about 1 petabyte in size, and it included all SAR data sets since 1978. So there was not a lot of SAR data available. But then only in a few years, we've grown by a factor of 10, almost a factor of 20. And then in the next few years, we'll grow another factor of 10. And actually by 2027, ASF will alone in our archives will house more bits and bytes of data than NASA currently houses in all of its archives combined. It's an enormous volume of data that's actually not easy for us to manage, and it's also very difficult for users to effectively still utilize. And that's one of the reasons why we have invested very heavily in cloud technology to allow us to manage these data sets effectively and give you as a user means to download and access these data sets quickly and easily. The other reason why making these data sets available to you in an easy way, the reason why it's complicated is also because SAR is an incredibly rich data set. So with every acquisition that we make, SAR data sets provide a variety of different sets of information. We have, of course, the amplitude information, which gives you an image of the surface, a cloud-free visualization of the surface. But you also have things like the polarization, which allows you to understand what kind of structures and surfaces are on the surface of Earth. And you have a phase measurement, which allows you to do interferometry. So the phase in the end is a proxy for the distance between the satellite and a point on ground. And we can measure how that distance changes with time in order to map things like volcanic inflation or earthquake motion at the centimeter level. And so all of these parts of the SAR signal, they actually use quite different technology and techniques to extract information from them. And we try to make tools and services available in all these areas to the user. And so to give you a little bit of an idea of what you can take advantage of these days is we have developed rich mechanisms for you to access data and also analysis-ready data services that allow you to create higher-level products automatically. And so we've made those available to the community to take advantage of this ever-growing archive. There's a QR code here. I'm assuming that you get the slides also, but if not, then you can just take a picture of that QR code. It gets you to our brand new website where some of these services are highlighted. There's a button on here that says services. So if you click on that, you get a little bit more information of all the tools that we have. The things that I want to talk to you about are 3 different things today. One tool is Vertex. Vertex is our search client that allows you to easily discover and download data sets. So search for them and download data sets. But integrated into Vertex is our value-added processing service that's called Hype. And Hype allows you to then take your data sets that you discovered and create a standard, higher level, level 2 type analysis-ready data products from them. So I'll talk about that a little bit too. And then we have another service that we call Open Science Lab or Open SAR Lab. And this is a cloud-based service that allows you then to work with your data sets directly in the cloud and not having to download data locally. And all of these services are to some extent available to you for free. I'm going to talk about that also as we go through. So our search client, Vertex, is accessible through this URL. It's search.asf.alaska.edu. Again, you can try to take a picture of that QR code, and that's also going to get you to the search client. It's a graphical user interface based search client that's driven on the back end by a Python search SDK and a search API. So you can search our archive either through this graphical user interface, but if you are a developer and you look for more programmatic access to data, you can also use our Python tools to search the archive through an API. So ASF allows you to search and discover all of our data holdings. When you come in, it's going to default to Sentinel-1, but you can search other data sets such as ALOS, such as some of our older data sets also through this archive. And through the same URL, you will also be able to discover nicer data sets once they become available next year. In addition to search of discovery, you can perform some INSAR data processing. So you can create your own interferograms automatically within Vertex using our value-added processing pipelines. And we also provide tools that allow you to build your perfect INSAR stack. So if you're familiar with INSAR time series analysis and tools such as short baseline subset INSAR analysis, we have some tools that allow you to configure your perfect INSAR stack directly in the platform. You can submit your Sentinel-1 scenes for on-demand processing, and we'll provide a set of value-added processes that I'm going to show you on the next slide. So directly through search, you can order value-added products, and specifically these three kinds right now. You can create RTC images. These are radiometric terrain-corrected images, fully geocoded and fully calibrated SAR data sets. If you are more an optical person, those are equivalent to what you would call a BRDF-corrected Landsat or optical image. So the data is fully calibrated, and the radiometry is corrected for sort of local slopes. And it's a super useful data set if you wanted to do time series analysis and change detection in an area from all the data sets that are available over a site. We provide these products. You can order them at 10, 20, or 30 meters. A lot of people, when you order them the first time, you opt to get the highest resolution possible. But you'll learn very quickly that there's a good trade-off between resolution and data volume, and sort of 10-meter products are still very large. So I think a good compromise between resolution and volume is the 20-meter product. We allow you to form interferograms. Interferograms use the phase differences between repeated acquisitions to analyze surface motion at the centimeter level. Interferometry, if you've tried interferometry processing yourself, is a very computationally intensive and time-consuming process. So we built some services that allow you to create interferograms at a 30 and 80 meter resolution automatically and very quickly in the cloud. And then a third service that we make available is called AutoRift. AutoRift is essentially a very clever glacier velocity tracking algorithm that uses spectral tracking to track features that are moving down glaciers. This is a service that was developed as part of the NASA Measures project and is available for you to use through ASF. I wanted to say that the service is available to you for free. Every user of ASF, everybody that has a username and login, can create up to 1,000 free such products per month. So either a mix of INSAR, RTC, AutoRift products up to 1,000 per month. Once you've created those, we also have a service that sits in a cloud that's based on Jupyter notebooks. We call it OpenSAR Lab. It's available at https://opensciencelab.asf.alaska.edu. Again, here's a QR code to get to the sign up page for OpenSAR Lab directly. Also, this is a service that's freely available to you. and it houses a Jupyter Hub and a Jupyter Notebook platform. Through this service, you can connect directly to the data sets, the application-ready or the analysis-ready data sets you created. So if you say you created 500 RTC images, you can connect to that archive, pull these data sets into a cloud-based platform, and then work with them in the cloud directly using Python programming and some of the notebooks that are available on the platform. So this is if you're a technology expert, a Kubernetes-based Jupyter Hub deployment that sits in Amazon Web Services. It sits right next to the archive. It's basically your computer in the cloud. It spins up automatically in a web browser, so you don't need to know anything about the cloud to then work directly in the cloud. When you start your machine, we auto pull in a repository of data recipes in a form of notebooks that you can utilize readily. So there are notebooks for INSAR time series analysis, change detection, etc., that you can use and modify to your heart's content. All of the data you create on OpenSAR Lab is persistent. So if you log out and log back in, all of your notebooks and all of your data sets will remain. And it provides a very flexible compute environment, anything from sort of the laptop scale computing to a HPC type computing work. What's nice about these services is they sort of build on top of each other, and they build a service chain that you can use to develop new prototype processes and bring these prototypes into production. So you can use our Vertex client and our existing ARD products to order, say, 1,000 products that you want to work with. You can then pull them into OpenSAR Lab directly to work with those. Then in OpenSAR Lab, you can develop new data analysis workflows, and you can mature these workflows in OpenSAR Lab. And then once you have matured them, we actually have a way via Docker containers to then deploy your workflows directly in our Hype service, in our automatic processing service, so that you can execute at very large scale. So it's a very nice thing to do end-to-end workflow development fully in the cloud. So the last thing that we do in this space, other than providing data and providing services, is ASF provides a whole lot of training in the field of SAR. It's something I personally feel very passionate about and have done a lot of. We do training at different levels. We actually were able to make formal SAR classes available to the community. So I teach 2 SAR-focused classes here at the University of Alaska Fairbanks. These are full semester graduate level classes. One of them is one on microwave remote sensing. The other one is one that focuses more on INSAR and other imaging geodesy techniques such as stereo processing, etc. All of the content of these classes is available to the public through these URLs. And if you want to take these classes for credit, you can sign up for these classes in the spring semesters. So I just finished microwave remote sensing this spring, and I'll teach the INSAR and its applications course next spring. In addition to those formal classes, we have built an edX 3-course curriculum program that walks you through SAR foundations. There's one course on hazard applications of SAR, and we are currently about to release a 3rd course on ecosystems. And so there's a 3-course curriculum program that you can also take. Beyond that, we do a lot of short courses. Some of the available ones right now, we have an upcoming short course this summer in collaboration with the EarthScope Consortium that's focusing on INSAR, especially using software packages such as ISINT MinPy. We have contributed to the SAR Handbook, which is a free and open available resource to learn more about the application of SAR for ecosystems work. We have a lot of material available on a website that's called Learn SAR. So if you can check that out too. These are summaries of workshops that we've done in the past and materials that you can download directly from there. We've developed a lot of ArcGIS story maps. So if you are a user of GIS, these story maps will tell you how to create value-added products using our services. And if you are attending the upcoming IGARS conference, for instance, that's happening this July, we have 2 tutorials that can help you get started with SAR at this conference. So we always jokingly say what our goal is. We try to help you go from SAR 0 to SAR hero. And so we have materials that help you learn about SAR. We have services that allow you to play with analysis-ready data products. We have services that help you develop your own algorithm and then scale them up in the cloud from laptop scale type computing to HPC computing. Lastly, we are very passionate about open science. All of our workflows that are available are fully open source. You can grab them on GitHub, replicate them on your local machine if you want to. We are very passionate about also helping you share your algorithm with the world. So if you have questions of how to share your work on GitHub, how to maintain work on GitHub, we can help you with that too. And we try to be very innovative with new data formats. So we are interested in helping you share your data sets as cloud-optimized geotiffs in modern data formats such as ZAR and Xarray, Stack, and so on. So if you have questions about those, please talk to us as well. I know I'm already a bit behind time, but let me at the very end give you a little bit of a flavor of some of the research work we do at ASF focused on SAR. I have 3 short examples that you might be interested in. The first one is a bit more application oriented. We have received some NASA funding over the years to take SAR and make it useful for hazard applications. And specifically, what we are working on is weather-related hazards. So through this work, we've developed some value-added products using actually the workflows that I showed you earlier. So we developed them in OpenSAR Lab and then deployed them in Hype for large-scale production. And so within, as part of this effort, we've developed the workflows we nowadays use for RTC image analysis and image production. We've developed an RGB composite from dual pole Sentinel-1 data. This RGB composite is designed to look and feel a little bit like an optical data set in the sense that vegetation should show up as green, water should show up as blue. And it for people that are not as familiar with SAR data, it makes SAR data a bit more easy to interpret. So those are available these days. We have then developed more quantitative products such as flood extent and flood depth. I'm going to talk about that a little bit more. And we've developed some change detection products there too. So the service developed these workflows, but it also deployed these workflows in the cloud. So we have developed cloud pipelines such as Hype that allow you to create these data products very quickly over large scales. And actually part of these research project developed OpenSAR Lab, which is the platform I showed you earlier and is now available for you to use. So all of these services were developed as part of research projects, and then we folded it into ASF's operational work. In terms of surface water mapping, so this is one of our quantitative products. We're using the fact that SAR sees or shows water in very particular ways in SAR images. SAR sensors always look somewhat oblique onto the ground in a sideways observation geometry, which is different from what you're used to with optical data. Optical data usually look straight down. SAR satellites always look to the side. This is because of the way the imaging process works. And in that side-looking geometry, if radar signals come down and hit a water surfaces tend to be high reflectance and very smooth surfaces. So they tend to scatter all of the signal away from the satellite, which means that your water surfaces always look very dark. This is different from other natural terrain. Other natural terrain has either some level of growth on it or some level of surface roughness that causes diffuse scattering and sends some of the energy back to the satellite. So natural terrain usually has some level of brightness in SAR images, while water surfaces are usually very dark. And we can use that distinct appearance of water to detect water using thresholding approaches. So this is an example here. What you see here is 2 image histograms So on the x-axis, we show the radar brightness in individual pixels. And on the y-axis, we show the frequency with which certain brightnesses appear in the image. So you see that there's a lot of pixels that have brightnesses of about -6, -7 decibels in the scene. And we have a second peak in that histogram that's about a -13 dB. And so you see that this data set has a bimodal distribution where you have one darker set of pixels that are on water surfaces and then brighter pixels that are on land. And you can define a separating threshold that separates pretty nicely water from land in this scene. So thresholding works pretty well to detect water surfaces. The problem with this approach is that there is not a single threshold that works for every SAR scene. So in this scene, for instance, the best separating threshold is about at -10 dBs. In this other scene, the best separating threshold would be at about -16 dB. So the approach that we developed, really all of the secret sauce is in how do you best define and automatically find the best threshold for every scene to separate water from land. And so we've developed an approach that does that. It ties the scene into different tiles and then uses those tiles to automatically try to find the best separating threshold for every image. And then uses that to map water. It does some post-processing to clean up the original water candidate mask. But in essence, most of the secret sauce is here in step 2, where it tries to automatically identify the best threshold for each scene. This is an approach that's very automatable. We have robustified this approach over the years. We have deployed it so that we can create water maps over large scales automatically. And if you go through to this URL, we actually have a partner in the Hindukush Himalaya. The partner is called ISPRS. They sit in Nepal, and they operate a service these days, a web interface that monitors surface water extent in the Hindukush Himalaya operationally all the time. We run the service for them, and they have a web interface to visualize the data for the community. And so the data set includes surface water maps. It includes a permanent water layer that shows you the water extent during normal conditions. And it also has a flood depth estimate in it that I can show you here in a sec. So you can use that in the Hindukush Himalaya to sort of look at the evolution of flooding, particularly during the monsoon days, but we operate the service actually year-round, so you can also look at flooding outside of the main monsoon. Just to give you some examples of what that looks like, this is in India, actually in the Assam province. This is a data set from last year. Here you see the water extent superimposed on the SAR amplitude image, and so this is an image I stole from Reuters from that exact time frame that gives you a little bit of a flavor of what that looks like on the ground with this particular water extent. And here's a separate example from that same day. This is a little bit more further south in Bangladesh, where there's in sort of northeastern Bangladesh, there are very large floodplains that develop. This is what that looks like from a satellite perspective. And on the right-hand side, you see what that looks like on the ground, a tremendous amount of surface water. In that project, we also developed a flood depth estimate. What this basically does, it takes our initially detected surface water extent and intersects it essentially with a DEM. And it basically says if this patch is covered in water, and if I know the topography, the local topography, I then can calculate notionally how deep the water has to be to flood this amount of terrain. This is a least squares approach that's running, an iterative least squares approach that uses what's called a basin hopping approach to find the optimal surface water depth effectively in an iterative least squares approach. And so this service is also running for the Hindukush Himalaya, and we did a little bit of validation on the water depth working with Bangladesh. So we compared our water depth estimates to the water depth estimate they get locally from river gauge data So here you see on the y-axis the depth from the gauge measurements, and on the x-axis you get the depth that we derived from SAR. And you see that those two are quite well correlated, with a standard deviation of about 1 meter, which is roughly what we expect based on the quality of the input data that we're using for flood depth estimation. So you can check this out. I don't have a QR code here, but if you get the slides, you can click on this link to get to the website where we monitor surface water extent in the Hindu-Kush Himalaya this way. More geophysically, one work that we are doing is we do a lot of monitoring of geophysical events in Alaska. Alaska is affected by a lot of geophysics. There's the Pacific fault that collides with the American fault in Alaska, and it causes a lot of earthquakes in our region and a lot of volcanic activity. And what I want to show you is some recent work that we've done last year on a volcano that's called Mount Edgecumbe. It's a volcano that's in what we call the panhandle of Alaska down here. And it was kind of a neat story because it took full advantage of the capabilities we have these days with systems like Sentinel-1 and with cloud-based platforms that we're providing to do a very large analysis of this volcano in very short time. And so what happened here is that in April of last year, a citizen of a town that's called Sitka, this is a coastal town here in Alaska, he used the services of the Alaska Earthquake Center and found that there was a curious earthquake that happened right under the edifice of this volcano. So this is where Edgecumbe volcano is located, and he saw there was an earthquake right under Edgecumbe, and he got curious about it. So he called up the Alaska Earthquake Center and said, like, hey, could this earthquake be related to volcanic activity? And it was very curious because Edgecumbe is a volcano, as you can very clearly see, but it hasn't been active in a very long time. In fact, this volcano was considered dormant at the time. Its last activity was, almost 1,000 years ago. So, but then when the Earthquake Center folks looked at earthquake activity at this volcano, they did discover that there wasn't only a single earthquake, but there was a really interesting earthquake swarm that happened very close to the volcanic site, and indicated that maybe this volcano is not dormant anymore. But this volcano is very poorly instrumented. There aren't any seismic stations nearby. This is partly the reason why the earthquake swarm shows up a little bit offset from the caldera itself, is that the location of these earthquakes is pretty poorly constrained because there are no seismic stations nearby. There's also no GPS, so we didn't know anything about the geodesy of this site. So the only thing we really had was INSAR. And we used our on-demand services to create a bunch of interferograms very quickly. And when we looked at some of these interferograms, and if you're familiar with INSAR, we saw this very distinctive bullseye pattern on the volcano in a single interferogram, which showed that there was a very significant uplift happening in actually quite short of a time. So this was a one-year interferogram that showed several centimeters of uplift at this volcano that we didn't know existed. So what we did is within only a few days, really within 3 days after this earthquake was discovered, we were able to run more than 1,500 interferograms using our automated services. We then discovered that there was significant uplift at this volcano. In fact, at the strongest uplift site, we have almost 9 centimeters per year uplift, which is quite substantial. It's one of the largest rates in Alaska right now. And it was also curious that the uplift started sometime in 2018, which coincided really well with the start of seismicity at the site. So there was a swarm in 2018 here, a larger one in 2020, and then several earthquake swarms since then that coincided very nicely with the start of the uplift at the site too. So we were also then able very quickly, using our open source tools, to then figure out what geophysically happens. So SAR is really good at giving you geodesy, so the geophysical information about uplift at the site, but it's not very good at giving you geophysics right away. So in order to understand the geophysical reason of the uplift. We had to do a source model inversion, and we used ascending and descending orbits for this. So we had two geometries to constrain the geophysics. And based on that, we found that most likely what happened was a combination of two things. We had an inflating a point source at a shallower location and a deflating sill at a deeper location. So most likely what's happening here is that magma was ascending from a deeper sill-shaped source into a more shallow point source. This is actually a relief. It means that while there's activity going on, we don't currently think that there's an imminent eruption at this volcano. And actually with that, I will stop here, I think, because I'm already over time, and give you a chance for more extensive questions. A third topic that I could talk about is on permafrost. So if you're interested in that, I can go back to it. And otherwise, I will end with my last slide, which hopefully you can still see. And so just summarizing that ASF is a very active data center where you can discover SAR data sets from some of the modern satellite missions, but you can also use a lot of value-added services directly at the archive. So please look into those, follow these QR codes to learn about our search client, to learn about our SAR services, and to sign up for OpenSAR Lab to then process data sets directly at the archive. And in addition to that, we do a lot of fundamental and applied research with SAR data sets. So I believe that our research group is one of the leading groups in North America to apply SAR both for geophysical applications, but also for more applied research on hazard monitoring specifically. And we do a lot of education and training. We are pretty good at posting our training activities, especially on Twitter. So you can use this QR code to connect with me on Twitter. I try to sort of propagate activities and new things in the field of SAR pretty effectively there. And so this is a good way of getting a hold of me and also following what's going on in the field of SAR. And lastly, if you want to email me directly, this is my email address, fjmeyer@alaska.edu. You can try to get a hold of me also via email this way. And with that, I will stop here and hope you have some interesting questions ready for me to answer. And I hand it back over to you guys.
Thank you so much. It was indeed a very insightful presentation. Just to summarize, we noticed in your presentation about various activities that Alaska Satellite Facility has been doing in relation to the application of SAR data and various case studies done using these data. And also it's good to know about various capacity building initiatives that your research group is doing for using SAR, that even include short-term trainings, credit-based course, and edX courses on SAR. So we hope these are really useful to our webinar participants, students, and professionals joining from different parts of the world. So I would like to thank you again for your for managing this webinar despite your busy schedule. And now, without wasting much time, I would like to go towards the question. And starting up, I would like to pick up some questions from Q&A first. And the first question says, what sets a NISAR different from the Sentinel-1 constellation, and how will it bring additional value to the research community?
Yeah, that's an excellent question. So it's a good question too, because Sentinel-1 has already done a tremendous service to the community. What Sentinel-1 provided to us is demonstrating that making data sets available freely and making them available at a regular plannable cadence every 6 to 12 days has really created a lot of research and a lot of interest around SAR. So NISAR is contributing to that in a few ways. One of them is it's going to continue this legacy that Sentinel-1 started of having freely available, medium to high resolution data sets that are observed globally all the time. So NISAR will also have an observation strategy where it will image all land masses all the time, and you will get data from NISAR every 12 days in the exact same geometry, and then from ascending and descending, depending on what latitude you are, at a higher temporal cadence. So in that sense, it's continuing and adding to this process that Sentinel-1 has helped us pioneer. What it adds in addition to Sentinel-1 is it operates globally at L-band, while Sentinel-1 operates at C-band. C-band is a wavelength that's about 5 centimeters long, so about year long physically, while L-band operates about 25 centimeters, so it has a longer wavelength. Now, how SAR signals interact with the surface is very strongly driven by that wavelength. And at the longer wavelength, say, if you think of a vegetation cover that's made out of leaves that maybe is about the size of a cell phone, a 5 centimeter wavelength will be blocked by these leaf structures, while a 25 centimeter wavelength has the capability to penetrate deeper into those vegetation covers. So that has two advantages. If you're an ecologist, the penetration into the vegetation actually allows you to have more interaction with the vegetation canopy. So it allows you to estimate things like above ground biomass of forests. It allows you to estimate things like canopy structure and changes of canopy structure over time. You can map agriculture extent, classify crops, all of these things. So it allows you to much more use SAR for understanding ecosystems. If you're a geophysicist, the penetration means that instead of scattering off of leaves and branches predominantly, you are creating a larger component of scattering that also comes from the tree stem and comes from areas under the trees. And it turns out that scattering from the ground under the trees and the tree stem is much more stable over time than the scattering that happens in the leaves themselves. You can imagine that leaves change fairly quickly. First of all, they grow seasonally. Secondly, if wind blows through the trees, those leaves move around all the time. And if you are an INSAR expert, if you want to use the phase to look at surface displacements, if we scatter off of leaves, this phase loses its meaning very quickly, or loses coherence very quickly. But if we scatter more underneath the trees, this scattering is much more stable, and we can measure displacements more accurately over much longer times using L-band. So there are those two advantages. The other advantage is that NISAR is actually going to be a 2-frequency mission, where over certain areas will operate both at L-band and S-band. And that's fantastic because it allows you to explore a much richer data set. Such missions haven't really been around much that provide more than one radar frequency. So that's another space how NISAR is going to contribute. Oh, and lastly, sorry, one more. NISAR is also going to be the first mission that provides level 2 data sets, so fully geocoded image time series and interferograms operationally directly from the mission. So with every new acquisition, you will get a fully geocoded data set that you can use right away in a GIS or in a cloud-based workflow. And you get an interferogram that you could use right away to analyze earthquakes or analyze volcanic eruptions.
Thank you so much. So the next question says, the application of INSAR in the Himalayas has always faced challenges due to the atmospheric delays. How can these challenges be minimized to enhance the effectiveness of INSAR techniques in this region?
Yeah, that's true. Because of the very strong topography in the Himalayas, atmospheric delay is a big issue. There are some means that you can use these days in publicly released software packages such as MinPy. MinPy allows you to use atmospheric models to try to remove some of the what we call stratified delays. There's a component of the atmospheric signal that tends to mimic topography, and MinPy has some capability to remove this component from the data. We actually working in this field right now to try to optimize INSAR for the Himalayas. And we are trying to optimize the correction of stratified delays by doing some additional correlation with topography with the phase. There's also some ways of using temporal models to try to also get rid of the turbulent atmospheric delay. So there's some tools that you can use nowadays in freely and openly. You may have heard of GACOS. That's a service where you can calculate atmospheric delays, and tools like MinPy, which is also open source, have some of these tools and capabilities in there right now. But we are actively working, our research group, on trying to optimize INSAR applications for the Hinekushima layer and try to fix out some of these remaining issues. Atmosphere is one, coherence is another that's really hard to come by in the Hinekushima layer. And we're trying to use modern sort of squeeze-SAR type approaches, so methods that use both point targets and distributed targets to also improve overall the amount of information we can retrieve on slopes in the Hinekushima layer. So it's work in progress in some ways.
Thank you so much. And the other question says, are there any applications based on SAR using ML techniques, as AI is leading nowadays? So maybe we can also, I'd like to add like how competitive it is to use ML techniques in SAR applications nowadays.
Yeah, so there's a variety of different sort of flavors of machine learning and deep learning that you can do. One of the ones that people have been doing with SAR is image classification. So there's some work on water mapping. I showed you sort of a more a thresholding-based approach, but there are also machine learning and deep learning approaches that do water mapping. We've developed recently some capability to automatically identify interferograms that have interesting fringe patterns in them. You could imagine if NISA provides an interferogram for every acquisition, there's a lot of interferograms out there. Not all of those are immediately interesting to you. And so we try to build some machine learning to identify highlight interferograms that you might be interested in. We are working currently on using SAR data sets to predict certain signals. Again, sort of thinking of the water mapping application, satellite-based water mapping gives you water extent only, of course, when satellite acquisitions happen. And even in the Sentinel case, that's only, say, every 12 days or maybe every 8 days over the Hinekushima layer, for instance. So we are trying to marry information we have from the ground, from river gauges and runoff information, which we have available continuously, and try to do machine learning to combine SAR data with the daily available water extent information from the ground to give you a prediction of water extent daily. So this is some work that's also happening using long-term, short-term memory deep learning models. We are trying to make some capability available to you through AWS resources like SageMaker, where you can deploy your model that you may have developed locally directly at the archive. So our data sets are located in AWS. SageMaker is an AWS capability, so it may allow you to take your model and scale it up without having to download lots of data. So that's some way how we try to support the machine learning and deep learning community.
Yeah. And the next question is, what's the reason for the same frame, same path, and same direction? Is the ascending node to have a slightly different sets of footprints for S1?
Yep. Yeah. So so usually we, as a community, think of the frame, or some call it frame, some other call it slice, as sort of the canonical footprint of an image. For Sentinel-1, that's actually not the case. The canonical unit of a Sentinel-1 acquisition is what's called the burst. It's a small patch of land. The way Sentinel-1 operates, it acquires basically small imagettes that we call bursts, and these bursts are actually fixed to the ground. So if you look at the same burst over time, its location will be stable and fixed. What ESA does, it usually takes about 27 bursts, so 9 bursts for the 3 subswars, and combines them into an image that they then call a frame. And unfortunately, which 9 bursts they're using is not always the same. So, they move up sometimes by a burst, sometimes by 2 bursts, and it causes that frame to slip up and down a little bit. So what we currently are doing is we try to provide you with a service that allows you to not search by frame, but search by burst ID, and then basically collect the bursts you want from the various frames so that the data sets you receive from us will always have the exact same footprint. So that's something that we are going to roll out over the next 6 to 12 months to help you a little bit stabilize the area that you're getting from Sentinel-1. But it's in the end because the collection of bursts that are combined in one frame is not always exactly the same. So they, depending on how they define it, it moves around a little bit.
Thank you. So then I have next question from Smriti, and it says, is there any possibility of getting on-demand product Sentinel service on DM developed in any other project?
You mean basically use your own DEM? Is that the question? I guess.
Yeah, it seems like that.
Yeah.
Yeah.
Yeah, so currently the automatic services that we have available allows you to choose between 2 different DEMs. It allows you to choose between SRTM, which was sort of our past standard, and now the Copernicus 30-meter DEM, which is a nice global consistent DEM. We've gotten that question a lot, can I bring my own DEM? Currently on the operational system, we don't have that available, but because our processing workflows are all public, you could, and we can help you with this if you email us, help you sort of deploy all of our workflows locally by cloning the repository and build it locally. And we have a Docker container for that too, if you're familiar with that. And then you can switch out the DEM to your heart's content. We are planning on making the DEM choices a bit more flexible in the future, but for now, operationally, we have those 2. If you want to use other ones, we can help you deploy and build our resources locally so that you can include your own DEMs.
Yeah, and then there is another question too. I guess we still have the planned time was for 1 hour, like maximum 30 minutes. I hope you still have some time, Dr. Meyer, maybe for
yeah, sure.
questions.
Yeah.
So the question says, sometimes using SBAS tool of Vertex, it shows gaps of information with Sentinel-1 data. How can it be solved? And the next question says, how can I cite OpenSAR Lab and on-demand infograms?
Yes. Excellent. So let me answer the second question first. It really puts a finger in a wound. So we've been very busy with rolling out all of these services to all of you, and we haven't been really good at catching up with publishing on them. There is citation work. If you go to the website and you go to the services, there's some information how you can cite it now. We have some conference publications related to that. But we are working actually on a peer-reviewed publication in OpenSAR Lab and a peer-reviewed publication on our on-demand services. We also have capability to help you with getting data on Zenodo so that you can get DOIs for different data sets that you create inside those. But we're working on the peer-reviewed publication for both of those services. If we have a minute, I could share my screen one more time for the first.
Yeah, definitely.
So I think what you mean is if you go in and let me just do an ESPA search real quick over California. So let's go somewhere here. So if this is your AOI and you want to do a search, say from 2018, January 1st to, let's do a year, 2019, January 1st. Let me find the frame. So it doesn't take very long. Okay, so let's say you did an ESPA search. Maybe you find this frame that you really like. Then you can go to this. Oh, I have to sign in. Okay, let me log in real quick. Then I can try to discover these data sets and do an ESPA search on them. And what can happen is, I think what you mean is once you find your time series, okay, so here's my time series, here's the interferograms that I found. So first of all, you see here this sliding issue that we talked earlier about. So this is because the exact collection of bursts that is being used has changed over time. If you form interferograms, by the way, to make sure that your interferograms are useful, I would, when you do an SPAS search, make sure that your images overlap at least 50%. So you can select sort of a minimum overlap requirement for your interferograms. And so you may end up with a stack like this, where every black dot here is a SAR acquisition, and every line is an interferogram that was selected based on certain SPAS criteria that you picked. So you allowed for up to 48 days in this case, and an unlimited spatial baseline in this case. If you want to avoid your SPAS stack to break up into different substacks, you could always manually try to add interferograms. There's a little plus button you can do to add additional interferograms to your stack, like this one, this dashed line. So I added an interferogram here. If you do that, it makes always sense to pick an interferogram that has about a 1-year time span. So we have January 1st to January 1st here, or say, what is this? Be June 6th to a future June 6th or so, to make sure that your entire network is connected. So you can always customize your stack by adding additional manual interferograms this way. And I'm not sure if that is answering the question. And then once you have your collection, you can then click on this little button to order all of these interferograms for your SPAS analysis. I hope that was getting to the heart of the question.
Thank you so much. So I'm just taking the question from our webinar form, and most of the questions are already asked. They were basically about applications of SAR, processing of SAR, and one of the questions that I think is still unanswered is about, okay, let me read it. How to access to high resolution data on SAR without paying for the data. Those of us in the developing world cannot afford to pay for high resolution data. So it was submitted through webinar registration form.
Yes, so we, ASF focuses predominantly on free and open SAR data. And as the person that asked the question noticed, that these open data sets are often lower resolution. If you want high resolution data sets, they're usually commercial and you have to pay for those. The commercial providers, first of all, they provide a very important service to the community by acquiring data at very high resolution. There's two ways how you can get access to free data sets through some of them. Many of these providers provide a proposal approach where you can get free access to archive data, historic, not the brand new data sets, but data sets that are older than a certain number of days, say maybe 2 or 3 or maybe 6 months, depending on the provider. I know, for instance, that TerraSAR provides such a service. If you Google for TerraSAR Science Server or something, you'll find a way of applying for getting free access to the archive. It's a very simple process. It's maybe a 2-3 page proposal where you have to describe, this is what I want to do with this data, and have to say a little bit the area of interest and how many data sets you're interested in. So many of the providers have this nowadays. Some of them have some sample data or some data that are freely available. The other approach is through the international charter. So if you are working in the field of hazards, for major hazard events around the globe, the international charter and the partners of the charter are required to make data sets over this site available for free. And so there are many freely available data sets this way. Maybe lastly, in the US, there's a consortium that's called WinSAR, which stands for the Western North America INSAR Consortium. WinSAR has collected high-resolution SAR data sets that were ordered by the community over time. You can sort of look at their archive and see where the data sets are at. And you also see which PI ordered these data sets. And you can then contact the PI to try to be added to the proposal so that you can access these data sets also. So there's a few resources That probably was too fast for you, but if you have follow-up questions, please email me and I can provide you some information on what's available in the space of high resolution SAR.
I think that's all regarding the questions. I'm just giving a last check to the chat box. It seems like, yeah, except introduction, I can see people saying, okay, Amrit says, I'm from Alaska and excited to listen Professor Franz.
Oh,
okay, he's thanking ISPRS for this initiative. Then we have ISPRS again saying it's very interesting to see the links of extra training. Yeah, so these are more about appreciation, and even in YouTube, I can see a person just commenting that he's from Uganda. So it seems like we have covered all the questions, and also we're right on time. So thank you so much, and I'd like to apologize again for the technical glitch that we had in the beginning of the webinar. And also, I'd like to assure you all that we'll upload this webinar session on our YouTube channel. So those of you who have registered but could not make it to this webinar, we will try to send you one common email with our YouTube link so that you can watch it again there. And also those who have attended this one, you can share the links with your friends as it is very useful. And our main aim is to share knowledge among students and professionals. Yeah, that's all from our side. So lastly, again, I'd like to thank Dr. Meyer for your precious time and information about SAR and all the useful resources. And if you share your slides with us, we will also upload it in our website so that everyone can access it publicly. Yeah, thank you so much.
That's good. Thank you all for being here, and greetings to wherever you're coming from.
Thank you.